and we are with some people who kind of know about virtualization. So introduce yourselves.
Who are you?
I'm Jim Day. I'm the Group Product Manager in Windows Server Marketing. We focus on server virtualization.
Great. And
I'm Mike Neal. I'm the Product Unit Manager for the Windows Virtualization team.
cool.
And I'm Jeff Woolsey. I'm a lead program manager on the Windows Virtualization team.
Cool.
Cool. So, I mean, the obvious question is, what is virtualization? What is virtualization?
So the area that virtualization is a big word.
Yes.
Sort of talking about there's a lot of different topics that sort of fall underneath that. The area that we focus on is an area called machine virtualization.
Okay.
And so we specifically look at providing a set of technology and solutions that allow multiple operating systems to run simultaneously on one piece of hardware.
Okay.
And so, as opposed to storage virtualization, where you may make a big pile of disks look like multiple disks, we're making a single physical machine look like there's multiple machines there to run operating systems in.
Cool. So, I mean, you're sort of like a kernel, in a sense.
Yeah, a lot of the technology that we deal with is at the kernel level, and in fact, we run below the kernel. And maybe a fun thing to do would be to go through a little bit of the architecture, but
Absolutely.
From an organizational standpoint too, we're in the same group as the core kernel and the operating system group. So we're under Rob Short in the COSD division.
We had him on Channel 9
Yeah,
recently.
yeah.
So, excellent. So what kind of products do you guys make? I mean, what are you working on? Virtual PC?
Yeah. So we have two main areas of focus right now. Virtual PC and Virtual Server are our products that are in the market today. Virtual PC is the client-focused product, so it's really focused at people running desktop operating systems.
Okay.
Virtual Server, as the name might imply, is really focused at people who are doing server and server consolidation work. And then we're also working on our next generation architecture, which is part of the Windows Longhorn release, and that is server-focused technology for doing virtualization as part of the operating system.
Cool. So now, one of the questions, so with virtual PC, you can run, I don't know, 60, 100 different operating systems, but there needs to be some sort of common architectural theme for the operating system you're running, right? It needs to be macro kernel based or whatever. There needs to be.
Yeah, and so the way that we do it is, and this may be a good time to just jump to the whiteboard a little
Please
bit,
do.
but the way that we do this is that we actually virtualize the underlying hardware.
Okay.
And so when we look at it, we have real physical hardware. And on top of that, we are going to run, typically you would run a kernel. And on top of that, applications.
Okay.
And that's the sort of normal stack that you would have. With the virtualization environment, what we do is we interpose what we call a VMM, and it produces a synthetic set of hardware. And so we emulate, today in the virtual PC and virtual server products, we emulate a full set of PC hardware. And so when you bring up the device manager inside of a virtual machine, you're going to see those synthetic devices. They're not going to be the devices that would be in the physical box. You might have an ATI video card in your physical box, but inside of our virtual machine it shows up as an S3 Trio 64, which is the device that we happen to emulate. And so on top of that we run the guest kernel, and we can actually run that no modifications. And then on top of that, apps that you would typically have within that environment, depending on whether it's virtual PC or virtual server.
Now, what do you look like on the machine that you're running on? You're just an application.
Right. So within that environment, we run virtual PC and virtual server have a component that runs in the sort of Ring 3 application space, but we also load this VMM driver. It's actually it is a kernel mode driver.
Okay.
And when we're running, we actually pull out the kernel that's typically in control of the processor. We actually pull that kernel off of that processor for a short period of time, put the VMM kernel, there's actually a kernel that's inside of the VMM, onto that processor, and let it run, and it runs the guest operating system within that environment. So that's the sort of sleight of hand that we do to multiplex the underlying physical resources. And then if something occurs that we don't handle within the virtual machine, we put it all back. We put the kernel back, and then we let the Windows kernel continue processing that.
Interesting. So what happens to the host operating system? So if you remove that kernel from the processor and inject yourselves, well, how does that affect the underlying system? I mean, can I do anything else while you're running?
Right. So again, we're doing it at a relatively fine granularity of time slicing. So you don't really know that from the host kernel's perspective, it doesn't really know that it was sort of pulled away and put back. And you can kind of think of it. There's a thread of execution that's occurring within the host environment, and we get called on that thread of execution and said, it's time for you to run. And typically that would be an application doing its normal workload. Instead of doing that, we just turn around and call into the VMM and say, okay, now it's time for you to take over the processor and do some work on behalf of the virtual machine for a while.
Okay.
And when the time slice runs out, or external interrupts occur, or a fault that occurs within the VM that has to exit out to the host and be handled, we again exit out of the VMM kernel, put the host operating system back in place, and let it run.
And so this is interesting because if in your virtual environment, if you're running an application and it does something that has a driver that runs in kernel mode for you in your your virtual kernel, you'll just crash like a normal application. You're not going to take down the underlying system.
Right, and so
that's a nice thing.
yeah, and that's a big chunk of technology that we have that we call ring compression. And so maybe just run through that really quickly. Is that if you're familiar with the x86 architecture, there's kernel mode code that runs at ring 0, and there's user mode code that runs at ring 3. And there's actually ring 1 and 2, but Windows doesn't actually use those.
Okay.
There are a few operating systems like OS2 use them, but for the most part, everybody just sort of made it a binary switch between user mode environment and a kernel mode environment. So within that host environment, we have ring 0 with the kernel running there, and ring 3 with apps running. When we run the guest environment, what we do is we run our VMM as ring 0. And on top of that, we run that guest kernel as ring 1.
Wow.
And then on top of that, we have the apps, and those just run as ring 3.
Okay.
And so what happens is that, if I'm a kernel mode driver, right, I usually have control of the whole machine. Like when you're running at ring 0, there's nothing you can't do basically, right? And so what we do is we promote all of that and run it at ring 1, and we run our VMM underneath that at ring 0. And so there's certain operations that this guest kernel or drivers may try to do, and in that process they're going to trap down into our kernel, and we'll decide, is that a legal operation? Can they do that? Or is it something that they shouldn't be doing, and thus we'll stop that VM from executing and sort of kill off the whole partition. If it's something legal, what we do is we sort of fake it up to look like it was actually occurring at ring 0 and let it continue. And so we always say that there's a whole bunch of code in the VMM that takes the guest kernel and makes it run at ring 1. And then there's a bunch of kernel code in that thing that fakes it so that it thinks it's running at ring 0. So it basically negates itself. And then the ring 3 stuff can just continue to run as we'd expect. And a lot of this has to do with this technique is because of the current architecture of the x86 processors. Intel and AMD have both announced and are shipping, Intel is shipping functionality to basically alleviate the need for this type of architecture. And as we move forward with the Windows hypervisor, we use VT, which is the virtualization technology from Intel, or Pacifica, which is the virtualization technology from
So could
from
you
AMD.
explain for the people out there why the significance of having the processor
Yeah. So
do the work?
So
Or
if I sort of compare and contrast between these two architectures, this is the architecture that's used today in virtual PC and virtual server. In the Windows hypervisor, what we do is, if I look at that sort of same type of drawing, right, I've got my apps here in ring 3, I've got my kernel in ring 0. What the hardware provides, VT and Pacifica, we always sort of internally refer to as ring -1. In reality, it's a different execution mode that could have ring 0 and ring 3 in it, but a good way to kind of think about it is that provides us an execution space down here, which we can run the hypervisor in, and you can kind of think of that as ring -1. And so instead of having to have this ring compression mechanism where there's a lot of software involved in making that occur, the hardware is taking care of a lot of it. And so for that other partition, we just run that kernel at ring 0, and we run those apps at ring 3, and the hypervisor provides, via the hardware, the isolation between there. So now if the kernel does something that it's not supposed to, we'll end up down here in the hypervisor. And we don't have to have all that code that goes, promotes it to ring 1 and then fakes it so that it thinks it's running at ring 0.
So that has a direct impact on performance, probably. Scalability.
It helps. It's interesting. The hardware is doing roughly the same thing that we were doing in software, right?
Okay.
So we did a lot of optimization work, for instance, to make Windows run real well in this environment. So it really it simplifies things to a great degree, and we look at it as less of an improvement at a performance level. We don't generally see a substantial performance improvement from that perspective, but it simplifies this layer of software, and really this is the root of the trusted computing base. This is really the lowest layer of software now in the system, and everything built on top of that needs to trust it. So we want this hypervisor to be very thin, and we want to keep it as simple as possible. And by using the hardware, that helps us keep that simple. So.
Fantastic. So what are the implications of this virtualization pattern in, say, the evolution of our operating system? I mean, it seems like, why not design an operating system with virtualization like this right off the bat?
Right. So obviously Windows, big code base, lots of features, lots of functionality. So our job really is, our team's job is to figure out how to fit this architecture into the current version of Windows. So even in Longhorn and Vista, we've made changes to the operating system. We call those enlightenments. So that the operating system is enlightened to know that it's running within a virtualization environment. And so for instance, in this environment, the enlightened kernel knows that instead of doing an operation, which normally would have to get trapped by the hypervisor, and then the hypervisor has to sort of intuit what it was doing. Oh, I didn't. This kernel executed this instruction to move to CR3, and had I have to figure out, did he mean to flush these page tables, or is he what exactly was the kernel trying to do? To do all of that takes a lot of effort, right? Because you've got to go and crack open the instruction and figure out what it was and try to figure out and try to optimize for those cases. Instead of doing that, we just tell the kernel you're running on a hypervisor. When you're going to do something like that, just call the hypervisor directly and have it do it for you. And so instead of trying to intuit and the implied behavior from the kernel, it's a very explicit call behavior that happens, and that produces significant performance improvements. So that combination of enlightenments, and we call those sort of core enlightenments. Those are the ones that really are happening at the kernel level. There's also enlightenments that we're doing on the I/O side. So I mentioned before, we emulate hardware today. In the future, we won't emulate hardware as much. We'll actually just produce synthetic devices that know that they're running within a virtualized environment and sort of optimize for that case.
Excellent.
So Mike, in that situation, those enlightenments that you've made, are they going to be applicable across any hypervisor, or is it just the one that your team is designing currently?
Right. So there are a number of vendors out there that are interested in producing this type of technology, and in particular there's an open source one called Zen that's really sort of shaping up to be the hypervisor that's associated with Linux, but it's potentially used by other people as well. And they obviously want to be able to run Windows in that environment as well. We're actually going to document this interface layer so that other vendors can potentially implement that as part of their solutions, and we provide the appropriate licensing if that's something that's necessary. So that enlightened kernel is something that can potentially work in those environments as well. The flip side of that is that the Linux community, as an example, and Solaris and others, are doing work as part of their operating systems to do their own set of enlightenments to talk to various hypervisors that are being developed as well, including Zen. And so we're trying to work with that community as well to make sure that we have good interoperability between all of those components.
Certainly.
Yeah.
One thing you may want to mention, Mike, is a question that comes up is when you're looking at the traditional architecture we have with virtual server and virtual PC, you don't need to modify your drivers or make any changes. And I've had a lot of people ask, when moving to this new architecture with Windows Virtualization, is there going to be a new driver model? Are we going to be requiring that? Is there some new certification?
So, and that's a real important point, is because this hypervisor box always has the hardware underneath it, right? And we have tens of thousands, if not hundreds of thousands of drivers in the Windows driver ecosystem. And one decision we could have made is that the hardware drivers, the drivers that talk to the physical hardware, could have lived either in a kernel inside of a partition, or it could have lived as part of the hypervisor. To put it down in the hypervisor, we would have had to change the way you write those drivers. And so there would have had to been this huge, massive porting effort to make that occur. The design that we chose, and actually the Zen folks have chosen that similar design as well, is that the drivers run within the kernel, within the partition. And so if I have a driver in here that talks to the disk, it talks through the hypervisor down to the disk, and you've got your little disk down here that it can then talk to. Now it goes through the hypervisor in a way that the hypervisor can determine should that partition have access to that physical piece of hardware. And so as we move forward in the architecture in the future, the interesting thing is the ability to what we call assign devices. So I've got a physical device here. I might assign those to one partition in sort of version 1, if you will. But in the future, we may have the ability to assign devices out to physical partitions across the machine. Regardless, you need some way to share a device, right? Today, people can run, easily 30 virtual machines on a 2-processor box. If you're in that situation, you don't have 30 Ethernet cards in a 2U rack unit machine, right? Yeah. So you need a mechanism to share those devices, and we use device emulation today, and we have a device I/O architecture for a virtualized device I/O architecture in the future. With the Windows hypervisor that provides that sharing mechanism.
Why would anybody run 30 VMs in one machine?
The primary driver, maybe Jim can talk a little bit about this, but the primary driver in the server world is server consolidation. I don't know if you want to elaborate, sort of, Jim, on what that.
Yeah, I think there's a lot of hardware that's out there today that's being grossly underutilized in the IT organization. So we're hearing customers say that they've got utilization rates anywhere from 5 to 10 to 15%. What they're trying to do is squeeze more efficiencies out of that hardware. So with the stuff that we're building, now you can start to pile on additional virtual machines. You can start raising the usage of each one of those physical machines by use of virtual machines. So now all of a sudden you're enabling faster turnaround, faster provisioning of new applications. You're enabling greater efficiencies on those hardware devices. So, and really in the future what you're going to see is you're going to have these really dynamic environments because of what this team is doing around encapsulating these virtual machines and completely isolating them. You can take these, which is today comprised of a single file, called what we're calling a virtual hard disk, and you can move those from physical machine to physical machine as long as they're running our VMM. And the cool thing about this that Mike and team are working on is that in the future, well, today you're running these VHDs on top of virtual server, but then tomorrow when we release the Windows hypervisor in the Longhorn Server Wave, you can take those VHDs and you can move them forward. So you've got a great forward migration path also.
Interesting. So that'll let me build new kinds of applications that use a lot of different machines in my enterprise that are just sitting there right now, or?
I wouldn't necessarily say you can use a lot of different machines, but what I would classify it as I can take these applications and I can create them in these virtual machines. So I can potentially customize them specifically for the virtual machines with the mindset of, in the future, being able to migrate them from box to box to box. In a lot of cases, it'll be independent of the underlying hardware. But I think that's going to be a great benefit to customers, because then, like in a disaster recovery scenario, where I might, in my production environment, have the latest and greatest boxes. But then in my disaster recovery environment, I might have some 2, 3, 4-year-old hardware where, in the old scenarios, I might be considering, okay, I've got to make sure that I've got compatibility for this stack in both this new hardware as well as this old hardware. Well, if I'm running a VMM, then potentially I can remove that limitation. And so it makes disaster recovery a really great scenario to run virtual machines in also. And then from a development and test environment,
Sure.
perspective, I mean, it's just phenomenal, right? The fact that, okay, I've got to test this N-tier architecture.
Right.
Do I go out and get N boxes, or do I get a virtual machine that I can now load up with all N-tiers?
I mean, you can literally, have a laptop and run, 4 or 5 virtual machines on it, and be able to test that architecture and your applications within that. And the VMs provide a lot of interesting capabilities, like we have, undo capabilities, so that you can basically take a checkpoint of the virtual machine environment and run for a while, maybe install some new software or try it out. You decide that didn't work, it's not, it's a bad build, or just, didn't meet your needs. You can stop the virtual machine and tell it to undo, and it will go back to that point in time, and it's like nothing ever happened. And so you don't have to re-provision the machine. It really simplifies development and test. There's a lot of great benefits there as well.
So let's talk about, that brings up a great point, compatibility, clearly. Also security. So for example, if I'm running in a virtual machine, then if I get rootkitted, it's going to be a rootkit in the virtual kernel, not in the core kernel. So that when I say close to that virtual instance, I'm not rootkitted anymore.
Correct.
And that's kind of an important, can we talk about building that into the security model of future operating systems?
And maybe I'll have Jeff talk about that a little bit, because he really drove a lot of the security work that we did for the virtual PC and virtual server releases. But you're absolutely right that the isolation is a key benefit that you find. So.
Isolation definitely. And as Mike mentioned when he first talking about the architecture is we're emulating hardware. So a common question is, hey, if I do get rootkitted, what does this do to my host operating system? And the answer is nothing. They are completely isolated. A virtual machine has no concept that it's running side by side alongside another virtual machine, or that it's running on top of a host operating system. And as part of the Microsoft security development lifecycle, we spent a lot of time working with the security team, top to bottom review, to make sure that when we developed this architecture that we could enforce and make sure that we did have that complete and secure isolation, so that a guest, for example, can't get breached, through a rootkit type thing that could eventually take over a host. You want to make sure that you can avoid that. So that definitely, it's definitely a very major focus for us. Let's talk about your question about compatibility. That's another very common question get asked about. What applications, can't I run in a virtual machine? And actually, the list is extremely small, because as Mike pointed out, we create a virtual environment based on, we actually based it and modeled it on physical hardware. So if you look at the virtual machine itself, and you actually go to Task Manager, Device Manager, and look at the hardware, it's a 440BX motherboard, an S3 Trio video card, an Intel Ethernet card, some of those common hardware out there. And we chose that actually from a compatibility standpoint to make sure that, when we want to install an operating system or an application or whatever, you're going to be able to find the drivers preloaded, pre-ready to go, and it's just going to work. In fact, one of the most common questions we get asked is, what did we do to limit the operating systems that you can install within a virtual machine? And the answer is absolutely zero. In fact, there's a website, I don't know it off the top of my head, where they've actually documented over 1,000 operating systems that they've actually tried and run with a virtual server.
Last time I talked here, it was 600.
No, it's over 1,000 now, and over 900 of them run just fine. And that speaks really well to the compatibility that we offer with virtual server.
It's interesting because we don't think about it as application compatibility. We think about it as operating system compatibility. Right? The majority of the applications run just fine. It's really if you have a dependency on specific hardware. So if you're running a device driver that needs to talk to a specific piece of hardware, obviously because we're isolating you from that hardware, that doesn't work. Right? So that type of thing won't. But as Jeff said, there's a vast number of OSs that just install and run within that environment and work within that. So.
Now, on the blogs and elsewhere, a lot of people are wondering, are you going to run the Macintosh operating system? Because now that Steve Jobs and Apple switched to Intel processors,
right?
Could you run the Macintosh operating system on top of Windows, or run Windows on top of the Mac?
Exactly. From a technology standpoint, there's two questions there, so I'll come back to the other one. But from a technology standpoint, there's really nothing that would sort of prevent that, right? You could produce a synthetic environment that would run Mac OS. Apple's made it very clear, though, from a licensing perspective, that they will not license Mac OS 10 for Intel to run on hardware other than their own, and this would be included as part of that. So from a respecting their licensing practices, that it wouldn't be something that we would try or even encourage. You ask another question, which is we have a a sister product, and the history of the virtualization technology at Microsoft is it really started with the acquisition of the Connectix Corporation, and Jeff and I were both employees there. And we had products today. The virtual PC product that we have for Windows was available from Connectix at that point in time, and we had Virtual Server under development. But we also had our product for the Macintosh, Power Mac, that allowed Windows to run inside the Power Macintosh environment. And so that's something that the Mac business unit is continuing to move forward and provide that functionality. And so they're working with Apple on how exactly they're going to accomplish that on the Intel-based Macs.
Yeah, I think I even have a video set up with,
Okay.
with the
Okay.
Mac side, because they announced at Macworld that they're going to support the Mac environment.
Yeah.
And they'll probably see a big performance improvement because now they're able to run right on Intel chips rather than have to emulate
Yeah.
back down to the PowerPC process.
Exactly, and in fact, it's interesting, the technology that we have for our Windows product now, obviously the Windows portion of our stuff, the things that actually, call Win32 and do the GUI and all that kind of stuff, that's not as useful to them. But a lot of the core technology that we've developed for both ring compression and running with the VT hardware is something that the Mac BU is very interested in. We still work with that team relatively frequently as well.
Now back on our side of the fence, we're this year supposedly going to release Windows Vista, right?
Yeah.
And Windows Vista, if you want the glass user interface, uses a more advanced card than the S3 card, right?
Exactly.
You need a 128 meg card today, and
Yep.
probably a little less when it gets released, but somewhere in that neighborhood.
Mm-hmm.
So will I be able to run glass on VM?
In current instances of virtual PC, you can't. It's the S3 Trio, so you get a 2D experience. We are planning in the short term an update for VPC for next calendar year. That will improve the experience, but it won't be the full 3D glass experience in that environment. Down the road in the future, as we sort of look at the client scenarios associated with the Windows hypervisor and the new architecture, we've been working with our graphics folks as well as the chipset manufacturers to really come up with a solution for being able to virtualize the 3D hardware and then be able to have the full rich experience in there. A lot of the people that use virtual PC today in their environments are business users who are running legacy applications.
Yeah.
They're typically using it because they need to have application compatibility and they need to run an older OS. So there's
Or developers who test.
or developers who are testing,
You
exactly.
need to test on 5 OSs,
Yep.
and
Yep.
why have 5 boxes? Just put
Exactly.
one box with 5 OSs.
Yep.
Right?
And so in those environments, typically being able to run with the sort of reduced user experience is not a burden.
So now, when you say, you can run 2 instances at the same time, multiple instances concurrently.
Sure.
Yeah.
So since you're proxying, all the in-flight I/O, et cetera, to where ultimately has to go
Yeah.
to some degree. So in other words, I can have X operating system here doing something. I could write an app. Is there a way for me to communicate from instance to instance?
Yeah, we provide a virtualized networking capability, and on the host side we have a virtual switch, and so I can add virtual NICs to the virtual machines, and some of those NICs can go and hook to real physical NICs so they can communicate out to the internet or your intranet or whatever. But I can also create what we call purely virtual networks, where they just talk between virtual machines, and there's no packets that ever go out on the wire. In fact, there's nothing really copied. It's just transmissions that occur back and forth between the VMs. And so you can use sort of standard networking technology to communicate back and forth between the VMs, and you can do it in such a way that it's isolated from the physical world. So, even in the server consolidation space, you see people produce N-tier architectures where they may have a database, a business logic, and web service, and they have those 3 pieces all communicate on a purely virtual network, and their database might be connected to their internal intranet, and then the web service can be on the other side of the firewall out in the DMZ or out on the wired internet,
Right.
and so that provides them a lot of capabilities to improve their security, improve the performance in a lot of cases, because that communication path isn't bound by any physical network speed.
Absolutely. I mean, you could run, as, again, it's hypothetically in the future, sometime, there could be an operating system where certain components are always running. So you always have virtual machines running, and you have your network-related stuff running in this virtual machine for security reasons, etc. You have your UI running in this virtual machine. They could communicate via this virtual networking infrastructure.
Yep.
I mean, it does have implications for the future of operating systems, which is very interesting.
Yeah,
It's very cool.
I was wondering, virtual machines were developed when machines were expensive, right? So for a developer, it was a lot cheaper to buy, a piece of software to run 5 OSs on
Right.
than to buy 5 machines.
Yeah.
Now the machines are getting so cheap that you can afford to do that, right?
Right.
And it's flipping around where the usage model now, like even my friends who are 21 years old who have blog services are seeing such demand for the machines that they're trying to figure out ways to virtualize banks of machines
Yeah.
into one space. Is that going to be something that your team is,
Yes.
buy 100 machines and run it as one machine? So
It's an interesting one. There are a couple of folks out there that's been some research in this area, and there's a couple of commercial products out there that are really focused on doing that scenario, which is to take a bunch of physical boxes and make it look like one big SMP box. And the interesting thing is that if you look at the types of applications there are today that actually scale well in SMP, there are very few. And really, if you look at the ones that scale up into the sort of 32 processor and above range, it really boils down to databases, right? And so the question is do you go buy a bunch of 2 processor boxes and then have to buy relatively expensive low latency interconnects, typically things like InfiniBand and stuff like that, to produce a reasonable architecture for you to be able to run it as a large SMP box, where the types of applications that you're actually going to run aren't all that practical within that environment. So, as an example, if you have a bunch of web services, right, and you've got these web servers that are your front end to your environment, you have a load balancer in front of that's directing out all the incoming traffic to those. You really have a scale out architecture. You want a bunch of boxes, and there may be limitations in that software that produces a situation where it doesn't scale well onto a large SMP box. So you may want a lot of little relatively small SMP boxes, 2-proc or 4-proc type environments. And virtual machines are a great use for that, where you can make more of those, right? And even though there might be contention within that single instance of the operating system that's really slowing it down, as long as there's 2 of them running on that box, and when one's not running, the other's running, you're getting a nice load balancing and a nice utilization of that underlying hardware. So we're not so focused on producing this, we kind of call it aggregation. It's this ability to take multiple boxes and be able to run them. The other thing that we're looking at is really when you look at the hardware roadmap, we're at dual core today, and we'll be at multi-core, quad core and multi-core as we progress down fairly quickly. And that technology is really going to drive the amount of capabilities. I mean, a 2-socket or a 4-socket system is going to have substantial computing power that there are not a lot of applications that can really take
substantial.
a whole bunch of
Can you imagine even dreaming of this world even 10 years ago?
Yeah, exactly. And one of the sort of challenges that the industry faces, and Microsoft I know is doing a lot of research and development in this area is like I said, there are few applications that scale into those multi-proc environments. Well, one of the other ones that really scales well is virtualization. Because we're really taking this big box and carving it up into little boxes, right? And we can schedule those things. The hypervisor has its own scheduler, and it can do a very good job of distributing those things across the resources that are available.
So do you only have? So in other words, I couldn't run. Let's say I had a 8-core machine. I'd still be running one hypervisor instance, or could I run 8?
You run a single hypervisor instance, but you run a large number of partitions, and each one of those partitions runs separate, what we call virtual processors. And so you could configure one of those partitions to have one virtual processor and it'd look like a uniproc box within that environment. Or you can create environments that have multiple virtual processors and it looks like an SMP box. And the hypervisor can do a very good job of deciding when those virtual processors should get scheduled and schedule them across any of the processing resources available within the physical system. And so that really provides a way to have a much more scalable architecture without having each one of the instances of the operating system and each one of the applications that's running in that know how to scale to a 32 processor environment. It takes a lot of effort to get an application that scales well on 32 proc, and a lot of effort to get a kernel that scales well. And Cutler and those guys have done a great job on building the Windows kernel to run within those environments.
Sure.
But hardware manufacturers coming to us who make a 32 socket system today and can put quad core processors in them, they're going to be at a point where they're going to need 128. And
Sure.
so what do they do then? Is the hypervisor the mechanism that they use? Is there an application out there that needs 128 cores? And like I said, there are very few.
Building virtualization into the kernel by default.
Yeah.
And then become a kernel component.
Yeah, and that's exactly what we're doing.
Is there anything that high-level developers like Charles need to do, way up here, to make their apps run better for virtual machines?
No, not in general. No, we try to do it at a level where the higher level applications don't really need to know about it. There was one area that you talked about, which was I could go out and buy a whole bunch of boxes, and what we find from customers is that you look at the and this is sort of the marketing term, but the total cost of ownership, right? And the initial acquisition cost is that amount that I go and pay for that physical box, right? But when you really sort of break it down, that's relatively small in comparison to now I've got this box and I got to hire somebody who's going to manage that box or a set of boxes. And if I look at the cost that I spend on managing that box for its 5-year lifespan or whatever it happens to be, that cost is so much higher. Virtualization, that's another area where app developers I think are going to get advantages from, because if you sort of have a set of if you've built your environment to scale out within a virtual machine environment, and your application sort of knows about that, the management costs associated with that can be decreased considerably as we move forward.
Yeah.
Our job up front with the server consolidation product is really reduce that acquisition costs, reduce the amount of money I'm spending on the physical hardware. I'm going to reduce the number of physical boxes and get it down to a consolidated set of OSs. I still have a lot of operating system images. Each one of those needs to be patched. Each one of those needs to be maintained. They need to be care and feeding is sort of the description that we use. If we can automate that, because it's inside of a virtual machine, if we can drive that from management tools, and we're working on those management tools, so that patch management and deployment gets much easier, and maintenance and backup and disaster recovery, all of those things get easier because they're in a virtualized environment. That's where we get that next layer of cost reduction for the customer. And the app vendor is sort of in there as well, because if you're an app vendor and you don't, and you tell your customer, I'm sorry, we don't support your applications running within a virtualized environment, you're doing your customer a disservice, right? That customer could be saving a lot of money and could be, incurring a lot of benefit by being able to do that. And Jeff, I don't know if you want to talk briefly about we went through and did this for all of the Microsoft applications. So.
Yeah, there are a couple of things. One of them, actually, just to loop around with what you were saying, is actually physical constraints being one of the key drivers to server virtual consolidation. We've talked with lots of customers and done a lot of industry analysis, and two of the things that come up are, one of them is just physical space.
Yeah.
We've talked to customers that say, server sprawl. I've not purchased hundreds, I've purchased thousands or tens of thousands of servers. I'm out of room. Where do I put these? For me to actually buy any more servers, I have to relocate, maybe a couple states away. Okay, so actual physical space is one. The other one is power. Power is just another key issue. I've talked to folks in, for example, Chicago high-rises that say, you know what, I've actually got plenty of budget to buy as many servers as I want. I just have no power to power them with. I go to the city says, you need to upgrade the grid. That's the types of problems that people are running into.
Oh yeah,
so
here at Microsoft we run into power and heat, right?
Microsoft, yes,
Heating,
power,
cooling,
cooling, it all comes back to, I have that server sprawl. I've got to be able to not only, stop it. I need to be able to slow down new development because I can't stop the current development, and I also need to be able to consolidate what I have. So that's one of the things that gets around the server virtualization. Another thing is actually support and making sure that your applications, actually supported within a virtual machine. Because when you talk with, some of your decision makers, they want to make sure that, if I'm running SQL in a virtual machine, that I'm really going to be supported from end to end. I can't call up Microsoft PSS and say, well, that's not supported, and not get any help. So one of the things that we did was we actually have been working as part of the Windows Server System organization, where all of the server applications that we have at Microsoft, things like Exchange, SQL, etc., they have a common engineering criteria. One of the things that we made sure on early on was that Virtual Server was part of that common engineering criteria, so that as teams release new versions of their products, for example, they're testing, they're developing, and they're making sure that their applications will be supported and work just fine within a virtual server, virtual machine. A great example of that would be the latest version of Exchange, for example. Exchange 2003 SP2, they just added support for Virtual Server. They made sure it was incorporated in all of the testing they've been doing to make sure it worked, and lo and behold, it worked just fine. And in fact, in part of that testing, we actually changed out a bunch of our internal Exchange servers here at Microsoft with virtual machines, and to see if anybody even noticed, and no one noticed. So MSIT was actually running multiple Exchange servers internally, and they were actually consolidating and doing some of this with Virtual Server, and had great results.
And we've run things like, some of the NTDev AD controllers are running inside VMs as well, and things like that. We run our. Yeah, no problem.
It's dark in that corner. Oh, we can see you now.
We also run internally our build system for virtual PC and virtual server run inside VMs. That we dog food our own. We internally use the term dog food for running our own products. So a lot of the teams internally use virtual machines in their test. Right? If you're doing localization testing is a great example. You got to run 23 different languages. You can just have 23 different VMs with each one of the different language versions of the operating system installed. Fire up a VM, test your application in it, throw it away, do an undo, and you're back to a clean, pristine OS image. You can run the next set of tests in the next day's build.
So let me talk a little bit about the server virtualization. So if I'm I want to have two different operating systems handling server, requests, which I can't quite see how that would work. But so I could have, Linux running, and I could have Windows running, and I would have Linux handle, I don't know, maybe it's running Apache, doing the web stuff. I could have SQL in this guy, and then they can communicate, right? And that's very interesting. Is that a scenario? I mean, it makes. It's an interesting scenario. So I'm just trying to think, how does that work? Could we talk about that a little bit? I mean,
sure.
How does that work?
Actually, let me give you a real-world example. I can't give you the name of the customer, but we're working with someone right now who has got multiple Windows applications that they need to consolidate, but they've got some old Unix applications that are actually very critical. It's actually part of their in-store business. It's part of their point of sale, as well as custom Unix applications, and they're considering moving into Windows, but they need a short-term migration path, and they're saying, well, why can't we just run these in Linux and run these in virtual machines? And they've actually been dogfooding this, trying this out, and actually they're finding out it's working pretty well for them, because they only have like 2 of these. The majority, everything they're running is actually Windows. I think it's like 18 or 20 apps that are Windows. They're consolidating, but there's these Unix apps, and there's 2 of them. And again, they'll probably look for a different long-term solution. But this is giving them a transition story for 18 to 24 months, where they can transition these in Linux, run them in VMs, and make sure that they have that story. And it's a real help from them, because they're actually going to go, looks like likely from 18 to 24 machines down to 2, where they're actually going to be running all of pretty much most of them on one, but they're actually setting up a failover with a cluster, so they can fail over VMs to a second in case something happens from a hardware perspective. And that actually, I was going to say, this actually brings us into one of the other things that people have been concerned about from a virtualization standpoint, which is the fact that once I consolidate, say I have 20 workloads, I consolidate down onto a single server, people are concerned, well, now the value of that single server has gone up tremendously.
All your eggs in one basket.
Exactly. It's all my eggs in one basket. It's single point of failure. What happens if someone kicks the power on that? Not just one workload goes down, but 20 of them go down, which is why we spent a lot of time in the latest version of Virtual Server to actually support clustering. So you can actually cluster virtual servers and the virtual machines. So if, again, I've got a virtual server running 20 VMs, all of a sudden I kick the power cord, all those VMs will automatically fail over and restart on a second node and automatically start up.
To your point, though, and when you kind of look at the architecture that we have, this might be a Windows kernel running in this environment, right?
Yeah.
This can be any other kernel. This can be Linux, right? And there's nothing, the environment that we produce is this sort of homogenized, virtual machine environment. It has this, sort of very common set of hardware. And people look at the hardware that we emulate and kind of, snicker because it's relatively old.
Okay.
But the idea there is that it's not constrained by any of the technology, right? It's, it may look like a 100 megabit Ethernet card, but it runs as fast as whatever the physical Ethernet card is that you have, right? It's not constrained by any sort of physical constraints anymore. It's just because it's all virtualized. So the reason we choose that older hardware is because we get a very broad set of compatibility. We can run everything back from DOS, Win3.1, OS2, 95, 98, and we can run all these different versions of Linux, BSD, Solaris, all those kind of things. And so that having that sort of very generic set of hardware provides us with broad compatibility right out of the box.
And so what those are really you're talking about, you just have a lot of drivers that you've stuffed into your
No,
your
in
application.
fact...
So what is, can you talk about emulation?
Yeah, so I can talk about that a little bit. So at the, sort of at the very basic level is, I might have an OS, right? And I've got a driver for, let's say, the networking card, right? So I've got my networking driver. Well, that driver is written, to the specific driver model of that operating system. So, if you go back to 95, it's sort of the VXD style, and you move forward to the latest versions, it's the modern Windows architecture. Linux has their own driver model, etc.
Okay.
But they're all talking to the same piece of hardware, right? At some point in time, somebody, Intel is the example, DEC originally built the Ethernet card that we emulate, and Intel bought that technology, and so it's now Intel branded. But this driver knows how to talk at a very low level to that physical, card, right? That Ethernet card that's connected out to the world, right? And there's a very low level, I/O ports and memory mapped I/O that are done to communicate that, and interrupts to indicate responses and DMA transactions and things like that. What we do is, instead of having the card do all of that, instead of that being all physical, we write a piece of software, that basically emulates this card's behavior. And so when this driver thinks it's talking to a physical card, it's really talking to this piece of software that says, oh, they read from this port. And so that means, they want to initiate a send. And so I'm going to do a DMA, and what I really need to do is go look in this other register and figure out what was the base of the memory for the DMA transaction, go and copy that data out, put it into the host, and then send that data out as a packet. Or I get a packet comes in, I'll assert a virtual interrupt into that environment, the correct interrupt, controller line, so that the virtualized environment, actually does that. So that takes a lot of effort.
It's a lot of
though.
engineering.
Yeah, it's a lot of engineering, and it takes a lot of effort. So every time I want to send a packet, I'm incurring this latency, right? I'm taking a little bit of time to go and do all of that work, and then produce that packet that goes out. And so as we move to the newer architecture, and we have the virtualized I/O architecture, instead of trying to emulate something, we're building an interface that's optimized for the virtualized environment. And so we'll decrease that latency considerably and improve the performance considerably.
And pretty much live to the true nature of a microkernel.
Exactly.
And which is really what you guys are.
Yeah, and that we
All
talk
right.
about this as being a microkernelized hypervisor, right? Because if you look at the hypervisor, if you sort of broke this apart and looked at the internals, right, you can kind of draw a line and say there's a bunch of stuff that has to do with virtualization. Above that line, it's I'm virtualizing the MMU, I'm virtualizing the APIC. There's these sort of constructs that are part of the hypervisor that really are focused on virtualization. Below that, it has things like a memory manager, it's got a scheduler, it's got all the sort of basic capabilities that you would find in a small operating system, right? And it's a complex one because it needs to deal with things like NUMA, right? It's going to be running on NUMA, non-uniform.
that?
Yeah, NUMA is non-uniform memory access architecture. So the basic idea there is that the amount of time it takes me to access a piece of memory isn't the same for every piece of memory. And so there might be a bank of memory that's directly connected to my processor that it takes less time for me to access than bank of memory that's connected to another physical processor, typically in an MP environment, that's further away, and it has what they call a higher NUMA ratio. So
Now this is new in Vista.
NUMA is actually supported today in 2003.
Okay.
And
Servers.
yeah, and it's primarily server,
Got it.
but even like a dual socket AMD box today is a NUMA architecture machine, because they have the memory controllers on the physical chips, and then an interconnect between the chips, and so you get slower memory access when you go to memory that's on chip number 2 from chip number 1. So that architecture we think will become more and more prevalent as memory controllers move to the core chipset for performance reasons, etc. The scheduler has to know about that. The tasks that are occurring on this thread of execution or this virtual processor are associated with this physical memory. And so if the scheduler makes poor decisions and decides to put that on a far away processor, on a different NUMA node is the terminology that we use, then you're going to get a bad performance. You're going to get not optimal performance. But if the scheduler is smart enough to know that and put those things together on the same processing node, you'll get better performance.
Now, very early on, I'd asked, we talked about briefly about what's the limitation of operating systems you run. You talked about x86.
Yes.
But what about an operating system like Singularity? You could run that in a virtual machine, and that's very interesting. How it would interoperate with your memory model.
So you'll note if you ever go and look at any of the Singularity research papers. In fact, I think the example driver that they publish is the S3 Trio 64 driver. And you'll wonder why that is, because nobody has one of those in a physical machine anymore. It's because they do the vast majority of their development inside of virtual machines today. So
Which leads to the next question: usability of your product.
Yeah,
building operating systems.
Exactly. So there's for the research that they're doing and the development of that architecture, doing it inside of a virtual machine is just natural, because it produces the environment that's similar to what they're actually, physical hardware that they're going to run on, but gives them all of those development flexibilities. When you crash a VM, it just crashes the VM. The host is fine, right? You can't, blue screen in here. You can triple fault. You can do whatever you want, right?
Yeah.
And it'll, maintain the host environment, and the other VMs will continue to run.
Which is
Yeah,
huge.
for somebody doing OS development, it sucks to reboot every 5 minutes, and you hard hang your machine, and you're like, what happened? And we actually internally have debugging tools that are built into our VM environment that help with kernel level development and things like that. That isn't something that we publish to the rest of the world, but it's kind of cool stuff for us to be able to use. So that's that's one of the advantages there. Singularity is a good example of a hypervisor and Singularity might make a good pairing, right? They have a different process model which doesn't use MMU as the primary isolation mechanism. They use the whole managed top to bottom architecture so that they can isolate their processes.
Yep.
But they still may want to have different partitions that do different things, that have different life cycles. So as an example, one of the things that keeps people from putting all of their eggs in one basket in one single instance of the OS is that they may want to reboot that from time to time, right? Exactly. And for whatever reason they may need to do some sort of maintenance, and they don't want to reboot all of their things simultaneously. They can make the decision to do them one at a time if that meets their business needs.
It's amazing. I mean, this is really. I mean, I keep harping on this, but this really is the path seems to be clear in the direction of the evolution of consumer operating systems.
Yeah.
Right? What you just said. Imagine I get an update to the virtual machine that my shell is running in. Well, I don't have to reboot my computer. Or parts of it.
Right.
I just restart it. Like closing an app, it restarts again. It's different than having to shut down and restart everything back up.
We look at one of the ones that we
It's
look.
extreme.
Yeah, and what we talk about isolation as one of the sort of primary benefits in the server space today, right? I can have multiple VMs that are running and they're isolated from each other. The interesting thing is you can combine isolation and other technologies to get to availability, right? Where let's take a client example, and this is just sort of talking about the future, right? Is that you might be able to run, for instance, your IP telephony stack in a partition. And if I want my PC to be my primary phone, right? How do I call tech support when Windows won't boot, right?
Yeah.
So if I have a partition that's a simplified environment and it's running just the IP telephony stack, right? I can pick up and make a phone call even though the OS image or whatever.
You're not talking about Windows Vista here.
No. This is
This is a
this
future.
is theoretical future.
Yeah.
Vienna or beyond, right?
I get out my crystal ball and look into the world. So I'm not making any product announcements for those guys. But I'm just saying that that's the kind of thing that you can kind of envision as you move forward.
Right.
The one thing that we're trying not to do with virtualization technology is we're not trying to cover up the sins of the past. There are things that we want to fix about the OS that you could kind of look at virtualization and say, I could use that as a Band-Aid. And maybe that's a good thing in the short term, but we want to fix those things and make them better. And you've had conversations, I know Channel 9's had conversations with the kernel teams about things like state separation and stuff like that. All of those things benefit us as, if VMs become less and less stateful, and we have good separation of state, we can move virtual machines around within the data center more rapidly. And so today you might migrate a virtual machine every time you need to do a patch or an upgrade or you're going to do some physical hardware. Well, if you get into an environment where you move them around because this machine has some resources available and your environment could be more efficient and run faster, and you can do that on a dynamic basis, that's when the whole DSI vision and what we call self-managing dynamic systems, that's where all of that stuff really kind of becomes real solid. And we're building all the foundation for that to get to that vision.
Clearly there's play back and forth, right? Work you're doing is positively affecting the work. I mean, what is an operating system? An operating system is a virtual machine. It virtualizes hardware, and you guys are also doing that.
Yep.
So you're learning things. They're going to take that. They're doing things. You're going to learn things.
Yep.
So there's this interaction where you're both evolving.
Yeah, and it's
Not
absolutely,
one replacing the other.
exactly, and it's absolutely why we're where we are in the organization. We're in the kernel organization because this is core OS technology.
To wrap it up, because we're almost out
Okay.
of time, will virtualization run better on Windows Vista on the client and Longhorn server on, compared, if you had two machines, will it run better on one, and if so, why?
So one of the things that we're doing that are part of Vista and part of Longhorn Server is that we're doing a set of enlightenments. And so when you're running in the hypervisor environment and you're running those on top of and you're allowed to use those enlightenments because you have those capabilities, that's going to improve performance. And it helps quite a bit for the initial testing that we've done. Obviously, we're still in development on this technology. But,
Yeah, sure.
So
There's all the other goodness, like better UI and better networking stack and better audio.
Yeah.
Does that matter to a virtualization?
Oh, yeah, because wherever the guest is more efficient about what it's doing, it's using up less resources of the machine that we could be potentially giving to another virtual machine that's running. And so efficiencies within the guest are always important. We work very closely with our performance team to make sure that the things that the guests are doing are efficient and the things that we're doing are efficient. But the change of the world with virtualization is that some things that are relatively inexpensive on physical hardware become fairly expensive in virtualized environment because you have to trap them and you have to do things to make sure that you're enforcing the isolation barriers. And those incur latency. They incur some amount of processing effort to do that. And so those assumptions that might have been made in the kernel or in other other sort of OS level software that says this is a cheap thing to do, it's not necessarily true anymore in the virtualized environment. So we work fairly closely with those teams to identify where those sort of hotspots are and help them optimize for that environment. So that's a lot of the testing that Jeff talked about as well. So
Perfect. Cool. Anything else? We have 2 more minutes.
I think that was good.
Yeah, that's great.
Covered a pretty broad range.
So I have one quick question.
Sure.
What language did you write your emulators in? Assembler or C++?
We are probably one of the last big chunks of assembly language out there. So we try to minimize it as much as possible because assembly language is pretty hard to maintain, and it takes it's really well documented code, but it's still a pain.
There's no code completion in your UI that you use to build it.
Yeah. So in the Windows Vista architecture that we have and Longhorn architecture that we have for this, there's assembly language in C in the hypervisor. There's C++ in what we call the virtualization stack, a little bit of assembly language in there as well. And we actually do our user interface, which plugs into the new version of MMC, is managed. So we actually use the
Can you
whole.
say that again,
Yeah,
please?
we use the manage from the top in the UI all the way down to assembly language at the bottom.
There's going to be managed stuff.
So-
shipping? All right. woo.
And it's again it's UI, it's the appropriate use of
That's
that
fine.
technology. One of the interesting ones is in this environment we have to do what we call binary translation. So we actually because we can't just execute those instructions directly, we actually look at an instruction stream and recompile it on the fly and produce a new set of. So we have not only assembly language in there, but we also have a compiler in there.
Wow.
So a very low-level compiler that does
But
binary
and those
trans.
streams of binary data you're getting are trusted streams.
It's a stream of it's the stream of instructions.
Oh,
So we're
stream of
looking
instructions.
at the instructions that the processor would execute
Right.
and translating those into a different set of
Wow.
instructions. So
Amazing.
The guys you work with are probably pretty smart.
we got some good folks. Eric Trout, our director, who is the CTO at Connectix, he's done just an outstanding job and great team. So
Sure.
yeah,
We do have some
really
openings,
fantastic.
don't we, Mike?
And we do have some openings.
So if you're really smart, you're working at.
If you want, feel free. If you go, what is it, VM Tech? If you go look for that in the job listings, we got openings all over. the place.
For developers?
Developers,
and
tests,
testers?
yeah, PM,
Okay.
everything. So
Fantastic. And since you cover the gamut, it can be managed developers or simpler.
absolutely,
Simply.
yeah.
Very
Perfect.
cool. Thank you very much.
Amazing
you.
work, you guys. This
Thanks.
is very cool.
Thought you guys
Cool.
liked-
Thank you.
Thanks.